So it's my pleasure to introduce Hulya Arguz from Université de Versailles, Paris-Saclay, who's going to give a talk on enumerating log maps via wall crossing.
Thank you very much for the invitation. It's a great pleasure to have the chance to talk here. So what I'm going to talk about today is joint work with Mark Rice. And my plan is to recall a little bit of what Gromov-Witten theory is and what relative and log Gromov-Witten theory is. Then I'll talk a bit of log geometry, log Calabi-Yau pairs, and mirror symmetry, and punctured log Gromov-Witten theory. Then I will tell you what has been done in the two-dimensional case in the context of mirror symmetry for log Calabi-Yau surfaces. And I will tell you what has been done about the tropical vertex that I will explain, and then I will explain the higher dimensional case, which we did in joint work with Mark. So I will talk about mirror symmetry for Calabi-Yau varieties of arbitrary dimension and about the higher dimensional tropical vertex. All right. So to recap classical Gromov-Witten theory, what you're interested in is this. You have a smooth projective variety X over C. You fix two things, two positive non-negative integers and G, and curve class beta in H2X, and then you consider the moduli space M bar G n X beta consisting of n-marked genus G stable maps to X of class beta. There are natural evaluation maps from this moduli space to X, which just evaluate the ith marked point of the curve. And to define the Gromov-Witten invariants, the last data you fix is some cohomology classes alpha 1 to alpha n, and the Gromov-Witten invariance of X is defined by integrating over the moduli space, the virtual class, the pullbacks under the evaluation maps of these cohomology classes. And the two main techniques to compute Gromov-Witten invariants are localization and degeneration techniques. And I'm mostly interested in degeneration. So localization works when you have some group action, you look at the fixed locus of this, and in degeneration, it's important to consider relative Gromov-Witten theory. What this means is so if you, in addition to the data to define Gromov-Witten invariance of X, if you fix for each marked point a non-negative integer mi, and to divide the d in X, then you can define the relative Gromov-Witten invariance of X as counts of n-marked genus G stable maps to X of class beta, such that f of xi has contact order mi, which you had fixed with the divisor d. And the theorem of Jumny in 2001, which is also worked in the syntactic setup by different people, Liruan and Ion Alparca, worked also relative Gromov-Witten invariance in the symplectic setup. A theorem of Jumny in 2001 in the algebra geometric setup is saying that if you have a family of projective schemes, you can degenerate your X, obtain a family of projective schemes such that your X degenerates into X1 and X2, two copies, glued along a divisor D. And then you can compute the Gromov-Witten invariance of X in terms of the relative Gromov-Witten invariance of these two copies relative to D. So this product is not what I'm going to go into detail, but there's an explicit formulation of how you can obtain the Gromov-Witten invariance of X in terms of these relative Gromov-Witten invariants. So that's a particular reason relative Gromov-Witten invariance plays a crucial role even while trying to compute absolute Gromov-Witten invariance. And I will tell a couple of words about what Jumny does to compute relative Gromov-Witten invariance. So in relative Gromov-Witten theory, you have the setup that you're looking at curves as illustrated in the picture, which have some given contact orders with D. The problem is, so you can imagine when you try to compactify your moduli space of such curves, your curve can come closer and closer to D, and some component of the curve might just fall inside D. And you may try to naively compactify your moduli space with these things which fall inside D, but that doesn't work well. So you cannot construct to make sure things worked well, you need a relative two-term perfect obstruction theory to construct a virtual fundamental class and so on. So if you consider things that fall into the divisor, this doesn't work. And what Jumni does is, rather than considering, to avoid considering curves that fall into the divisor or whose components fall into the divisor, he expands the target. So he's creating bubbles, which are P1 bundles over the divisor D, and rather compactifies with the modular space with curves which live inside the bubbles and which don't fall into the divisor D, like on the right-hand corner picture. So if you contract the bubble that I drew again, which is a P1 bundle over D, you will obtain a curve which falls inside D. And he's showing that after finitely many bubbles, which he calls the accordion picture, you can obtain all curves you need to have a nice moduli space. So it is based on, the idea is based on expanding the target. And this works whenever you have a smooth divisor D. And what Gromov-Witten and Abramovich-Chan does works in more generality. It works for any log-smooth divisor, which includes cases like normal crossing divisors. And what they do is they record contact orders without expanding the target. They don't modify the target. They rather introduce the additional data given by log structures, which I will talk about in a second. So the idea is, if you have a contact order, if you have a point P on your source square mapping to f of P, and it has a contact order with your divisor D, the idea is to record the contact order by some maps of monoliths, which are log structures, which we denote by M bar X. By this map UP from M bar X, f of P to M bar CP to natural numbers. So the image of this map will be something, will be an element in natural numbers, and it will be the contact order. So imagine you have a map sending 1 to 5, and the contact order is 5. So you record contact orders by looking at such maps. All right, and I will describe what these maps are, what these sheaves are. So M bars are some sheaves which define log structures. So this has the advantage that it works in more general setups and you don't modify the target. And there are nice maps between all these modular spaces of Gromov-Witten, Abramovich-Chan, and Jumni, which I worked by Abramovich-Witten. So I will focus on log geometry, how we do this description of relative maps. A log structure is a sheaf of monoliths together with a map to the structure sheaf, inducing an isomorphism on the invertible elements of the structure sheaf. And the log scheme is a scheme with a log structure. What I was denoting by M bar is the sheaf of monoliths, which you quotient out your sheaf M by the invertible elements of your structure sheaf. And one advantage of log geometry that it behaves well. You can tropicalize log schemes and turn a log problem into a tropical problem, which is nice combinatorially. So the tropicalization of a log scheme is defined just by considering the Gauss sheaf, the discrete part. And this is it's defined as a cone complex, which is given as a union of cones given by homomorphisms from M bar x eta, where eta is a generic point, to r greater or equal 0. And then you need to identify these cones. So there are some identifications induced by generalization maps. I will give some examples. So if you look at the basic and most important example of a log structure, it's the divisorial log structure you define whenever you have a divisor D and its complement is included in X by a map J. You define your sheaf of regular functions which are invertible away from D. And this describes your log structure. There's a natural inclusion map from MX. For instance, if you look at A1, if you look at the stalk of your log structure at 0 of A1, if the coordinate is t, all functions that are invertible away from 0 are of the form some invertible function times t to n. And what it means to look at the ghost structures, you just forget the invertible function, you just have t to n. And the ghost structure is naturally isomorphic to the natural numbers by mapping 2 to n by just considering 2 power. It's similar to logarithm map, so it's a log structure in some way. Another example of a log structure is a log structure on a point, a standard log point. You can consider the point spec C, you can consider define the sheaf of mono and C star direct sum n, and define a map from Mx to your structure sheaf C by mapping a pair xn to x if n is 0 and 0 if n is not 0. And this will appear often because this is a natural log structure that comes from the log structure of A1, and there is a natural way to pull back log structures whenever you have a subscheme. There's a canonical way to pull back. If you take the name pull back, the log structure doesn't immediately satisfy the condition that it needs to restrict to an isomorphism on invertible elements, but you take some fibered coproduct, quotienting out to make everything nice, and this standard log point is just a pullback of the log structure to 0 of the above log structure. Okay, so if you have a log Calabi-Yau pair, which I will define now, it admits a very natural log structure because you have a variety x and a divisor d, so there's this divisorial log structure we will consider. A log Calabi-Yau pair is given by a smooth projective variety over C and a simple reduced simple normal crossing divisor in D and X, which is anti-canonical. And we will denote the irreducible components of D by Di, and we assume that our log Calabi-Yau pairs are maximally degenerate, which means that there exists some index set J such that Dj, the intersection of Dj's of some components, is non-empty and zero-dimensional. This is a technical condition which ensures that when we take the tropicalization of the log Calabi-Yau pair, when we define the tropical log Calabi-Yau pairs, it will have the same real dimension as the complex dimension of X. So if you look at a smooth projective toric variety and its toric boundary divisor, the anti-canonical divisor in it, this will be a natural log Calabi-Yau pair. It will be not terribly interesting there. So the log Calabi-Yau pairs you will be interested throughout this talk are given by blow-ups of toric varieties. So if you fix general hypersurfaces H1 to Hs in the toric boundary divisor of a toric variety, and if you blow up this toric variety along these general hypersurfaces in the toric boundary divisor, then you obtain a natural log Calabi-Yau pair given by this blow-up and taking the strict transform of your boundary divisor. And this gives a maximum degenerate log Calabi-Yau pair, and we will be interested in computing punctured log Gromov-Witten invariants of such pairs, and we consider the usual divisorial log structure always whenever we talk about log Calabi-Yau pairs.
In this last example, you take the union of the hypersurfaces, not the intersection, right. The union.
Yes, I take the union of general hypersurfaces. So I can have different hypersurfaces and different toric boundary components. I'm assuming
it's coming up.
It's coming up like the classical example. I will assume you have like P3. The toric boundary divisor consists of 4 copies of P2, and I can have a line and 1 copy of these P2s and another line and the other copy of P2. So I will blow up along these 2 lines.
Okay.
Oh, so they are hypersurfaces of the divisor.
Right. Okay.
Yes.
I was confused by that. Yes. Okay.
Yes, they are hypersurfaces of the divisor. Exactly. Right. Thank you. So when I want to work with log schemes, convenient ways to consider their tropicalizations, can apply the description of tropicalization of a log scheme that I just said. And if you tropicalize a Calabi-Yau pair, what you obtain is just the dual intersection complex of it, which is described purely from the intersection data of your divisor du fix in XD. And we will denote the tropicalization by B. It admits a natural polyhedral decomposition P. For instance, if your Calabi-Yau pair is a toric variety, P will be B will be the support of the toric fan, and P will be the natural stratification on the toric fan. And we define an integral structure on this tropicalization away from the zero strata. And this is the example of a tropicalization of dp7 on the left-hand side, which is the blow-up of P2 at 2 toric points, and the tropicalization of dp5, which is the blow-up of P2 at 2 toric plus 2 non-toric points. There's an integral affine singularity in the middle. So you can think of the tropicalization of, in the toric case, as a toric fan, which is just due to the momentum polytope, which I drew small above here on the left. And there is a description of almost toric-based diagrams, which play the role of the momentum polytope for non-toric varieties, like if you blow up non-torically, by Margaret Symington in dimension 2. And if you just take the dual, so there are these integral affine singularities. When you blow up non-torically, you introduce singular fibers, and then there are these singularities you introduce. It produces a natural singular integral affine structure. And you can describe the singular integral affine structure by just purely looking at the intersection pattern of these DIs. So if you want everything, when you blow up at 2 toric, 2 non-toric points, you get 10 minus 1 curves. 5 of them will be will be the strict transforms of the toric boundary. And if you want everything to be of -1, you cannot close up. You need a singularity. Like if you put the, so there is a way to compute intersection numbers of a divisor using toric geometry. And so the self-intersection number of a divisor is just minus, if this divisor is the sum of the 2 neighboring divisors times k, minus k is the self-intersection number. And if you follow that pattern, you see that you cannot close up. You need to introduce a singularity. So there's a natural way to introduce an integral affine structure with singularity on the tropicalization. And this is where everything scattering and wall crossing will live at.
Sorry, Hulya, we're always in dimension 2, is that right? Or?
No, everything in the first part of the talk lives in dimension 2. Everything we did with Mark works in higher dimensions. Okay. So we introduce integral affine structures and singularities in higher dimensions. We describe those. Okay. So
but for the moment, it's dimension 2, right?
Sorry?
But right now we're in dimension 2.
Right now we're in dimension 2, yes. Right. So, and you're right. I mean, in higher dimension, when we introduce integral affine structures, they will be only away from codimension 2 locus of the tropicalization. Right. So if you look at Calabi-Yau pairs, and if you want to understand mirror symmetry for them, if you have a Calabi-Yau pair XT, its complement x minus t is an open Calabi-Yau variety, and SYZ mirror symmetry says that if you look at this open Calabi-Yau variety, you should have a natural mirror, which is another Calabi-Yau variety, and you can construct this mirror by looking at counting Maslow index 0 holomorphic disks with boundary on some SYZ fibers. And what Gromov-Witten do is an algebra geometric realization of this idea. So rather than looking at Maslow index 0 disks, they look at punctured log maps. They trade these by punctured log maps. And using these punctured log maps, they construct a canonical scattering diagram. And using this canonical scattering diagram, they construct a homogeneous coordinate ring of the mirror to a Calabi-Yau variety, which we will see. Okay. So for xt toric, u will be the complement, x minus t will be just t star to n, which admits a smooth background in torus vibration. There are no Maslow index 0 disks, then the canonical scattering diagram will be just trivial, and the mirror will be just c star to n. But an interesting case we are interested in, if you look at the blow-up of hypersurface in the toric boundary, U is no more C star to N. The Lagrangian torus vibration necessarily has singularities, as we mentioned. And there are non-trivial mass index zero disks, and the canonical scattering diagram will be very non-trivial. And what we show with Mark Cruz in our paper we completed this year is if you have a log Calabi-Yau variety XD obtained from a toric pair by a blow-up in its toric boundary, then the canonical scattering diagram, it meets a complete algorithmic description, and I will tell what this algorithmic description is. So without reference to the enumerative geometry of XD, you can purely algorithmically describe what this canonical scattering diagram is, which gives you a way in particular to obtain all enumerative geometric information algorithmically, purely combinatorially. Okay, so by definition, the canonical scattering diagram attached to a log Calabi-Yau pair consists of pairs rho f rho, where rho are walls, which are codimension 1 cells of the tropicalization, and f rho are wall crossing functions attached to walls, which instruct how to transform monomials across these walls. So if you have a usual toric variety, you have affine varieties. You can associate to each of these two-dimensional cones of B. You see in this figure like spec C, X minus Y, and so on, and then you patch them together. When you have the right-hand figure, you have again some affine charts, and you want to patch them together, but non-trivially, there will be on each of these rays some wall crossing functions telling you how you're gluing together all these monomials and building algebraic variety at the end of the day if everything is consistently glued. And in dimension 2, wall crossing functions are determined by counts of log maps, and in higher dimensions, sorry, this is higher dimensions, they are determined by counts of punctured log maps, which we will see. So I will tell you what log maps are. We are looking at SMS, a log point which we had mentioned, and X, a log scheme over S, and in applications, SMS will be either the trivial log point or the standard log point, which means in applications, you can look at absolute invariants, or you can look at degenerations, and you can look at invariance of the central fiber of a degeneration, in which case your S will be the standard log point. So there will be a difference on the setup you're working with, what you take to S. And a stable log map is a commutative diagram from a curve C endowed with a log structure MC to X endowed with a log structure MX, where C admits a log smooth map pi to WMW, where WMW is a log point and SMS is the base of your target. Okay, and you require the underlying map of schemes C to X to be a stable map. So you have a stable map where you endow everything with log structures, and you require your domain to be log smooth over some log point. Log smooth means locally pi is induced by a morphism which looks like a morphism between toric varieties. You have like toric monoids. And the local structure of MC, what is MC you consider, you can define it, and the work of Fumiharu Kato, this is described by from the condition that pi is log smooth. Once you know what W is, once you know what pi log smooth is, you can describe the stalks of your log scheme, and these are classified by the theorem of Kato. Okay, so I will define the combinatorial type of a log map, C over W to X over X. This consists of a dual intersection graph of C, where irreducible components correspond to vertices of the graph, nodes correspond to edges, and marked points correspond to unbounded edges, which are legs. And there is a genus function from the vertices associating to every vertex a genus, and there is a map from the union of vertices and edges and legs to the tropicalization of C, mapping any X and C to M X f of X dual. It is like the contact and there's the contact data UP, which is M bar dual, which is hom M bar to natural numbers, the Gauss sheaf. And similarly, you can define contact data for marked points and nodes. So this is technical description, which I will not go into too much detail. The reason why I'm telling this is, given a combinatorial type, what you can do is you can construct a monoid of a stable map. It's purely constructed by defining this monoid, which is called a basic monoid, Q. You can construct a basic monoid by constructing its tool, and you construct its tool by looking at sum of monoids. So it's the sum of monoids. For every node Q, you take a copy of natural numbers. For every irreducible generic component eta in your curve, you take mxf of eta dual, and you have some relation imposed by the contact order. So this is the basic monoids, and this basic monoids depends on the combinatorial type of the map, and given a stable log map, one can show that there is a canonical map from this basic monoid. You can construct purely from the combinatorial type to M bar W, where you remember we impose our curve, the source curve, to be log smooth over WMW. And by definition, a stable log map X to X is said to be basic if the natural map of monoids Q to M bar W is an isomorphism. So why am I describing all this technical stuff? If I lost you, don't worry, it will not be terribly crucial. Although I want to say this because this is the heart of Gromov-Witten theory. This existence of a basic monoid, this construction of the basic monoid, plays a crucial role. So the idea was to replace everything Jumni needs. Like in this picture, you remember Jumni has all these bubbles, and he shows there are finitely many bubbles. And how many bubbles you need depends on how many nodes your curve has, what the contact type is, and everything. So you want to record all this data in your sheaves, and all this data is encoded in the basic monoid. So you construct a basic monoid that sees all the topological data that Jumni needs, and you record everything in your basic monoid, and you ask your source curve to be smooth over some basic monoid. And so the theorem then says, if you look at the modular space of basic stable log maps with target X over C, then this is a nice Deligne-Mumford stack. And you can do enumeration, and everything is nice. So you look at this basicness condition is important, and what's punctured stable log maps do. So if you generalize the theory of stable punctured maps, there's a generalization provided by Gromov-Witten and Cross-Ebert, where the contact data is allowed to be negative. So you modify your Gauss sheaf. So you look at maps not to natural numbers, but to integers. So you allow negative contact orders. Geometrically, what does this mean? So if you look at this picture, they correspond to, in the expanded degeneration. If you look at this picture I drew here, this curve does not hit really the divisor D. And if in relative Gromov-Witten theory, if on one side you hit the divisor D, on the other side you want to hit it at the same point, and one some kissing condition, and at those points you hit. But in punctured Gromov-Witten theory, there can be curves that come to your divisor, and on the other side there can be nothing. So there are some descriptions what punctured log maps correspond to in the expanded degeneration provided by some Chinese group of people. So what Gromov-Witten and Cross-Ebert prove is if you have a proper log smooth moduli space of genus Phi basic stable punctured maps to X over S of class beta and contact data U, this is a proper Deligne-Mumford stack. In the nice cases, everything we consider will be nice cases. The moduli space admits a natural virtual fundamental class. So they expand everything done in Gromov-Witten theory to this punctured case. All right. So Apologies if I lost all of you. Now I will tell how we use, once we have all these nice moduli spaces, and if we can compute invariants, how this is used to construct coordinate rings of mirrors to local Calabi-Yau varieties. I will first tell the two-dimensional case, and then what we did in higher dimensions. The problem in two-dimensional case is this: we consider very specific types of low Gromov-Witten invariants to construct the canonical scattering diagrams. So the low Gromov-Witten invariants we consider in dimension 2 are these. If we fix beta in H2x, a two-dimensional cone in the tropicalization with rays with primitive generators corresponding to divisors di and di plus 1. And I will denote by mi the primitive integral vector generating these rays, and we fix v a mi plus b mi plus 1, where a, b are non-negative integers. Like I illustrate a, b here inside in the interior of the cone, they can also be in the rays. So if a or b are non-zero, these rays will lie in the rays of my picture. And I denote by mv beta the number of genus 0 log curves in X of class beta which intersect T at a single point with multiplicity A and B. So if you look at the blow-up of P2 at 2 toric plus 2 non-toric points, which is admitting an almost toric-based diagram that I drew on the right-hand side, you can see that there are 10 minus 1 curves. 5 are coming from the boundary, the strict transforms of the boundary components, and there are 5 markers which are like obtained. I drew them like this, like E1 is a curve which, so there's a singularity over the tip of the red triangle, which is pinch torus. So dp5 admits the torus vibration over this picture. And over there are, in the interior, there are 2 singular torus fibers, and you can use some conormal bundle construction to construct minus 1 curves, which are curves over these that I drew E1 to E5, and those 5 minus 1 curves correspond all to curves which intersect the boundary at one single point, and they correspond to these 5 rays. And in the special case of dp5, if you fix a ray in the interior of a cone, there are no curves that would correspond to those. So there are no curves that all curve intersects the boundary generically in the interior. So if you have any AB like I drew it in the interior, and if you impose the condition of a log curve to intersect the toric boundary at a single point with intersection AB, it needs to go to the intersection of 2 boundary components. But there are no curves in this dp5 example, so the tropicalizations in some way of all these 5 curves will be like rays, these 5 rays.
I'm a little confused by this picture. So when you have this E1 up to E5 on the right-hand side, that's like the polytope for the toric picture, right?
Yes.
Is that the image of some curves on the total space that somehow project onto lines?
Yes, that's true. I just drew this picture because I mean, usually you're absolutely right, we don't draw curves on the momentum polytope picture. I just drew it for convenience to illustrate it better, but what you say is right.
I see. So like on the corners, every time it touches a corner or a line in the red thing, that means that there are some cycles that degenerate, and therefore these lines that here look like they would be things of boundary, they pull up to something that can be closed up at the ends and then become P1s or something,
that's
right?
Absolutely right. At some point, honestly, we were interested to find an affine geometric description of the Mori cone by using purely the affine geometry on the cone side. During my PhD, we could never complete that. So we were drawing these pictures. So if you really blow up, if you take a configuration of 10 curves in P2, 2 like this, and 2 from the corners, and if you blow up the corners, you get your 10 minus 1 curves. 4 the exceptional divisors and 4 from these and 6 from the strict transforms of these things. And the DIs and EIs are these 10 minus 1 curves, and if you take a configuration of 6 lines like this and blow up at the corners.
Right.
And the intersection pattern is the Peterson graph. So I was trying to draw these EIs such that they respect the intersection pattern. Each EI intersects DI at one point, and each EI intersects 2 other EIs. So it needs to it needs to be like this. So like if you look at E1, as you said, fiber gets contracted and it intersects E3 at this tip, and which goes here, and E4, it intersects T1 only at one point. So by just looking at the intersection patterns,
Right.
there's
And when just so, because some curves are more complicated than others, the E4, for example, it comes from an edge on the top right.
yes.
Then it touches the vertex of the red triangle, so that's a pinch. Is that correct?
Absolutely correct. And there is some subtlety that's, yeah, you're absolutely right. This picture, there's some subtlety in this picture. So as you said,
it's okay. And then it goes all the way to
like to the left, E2 goes down, E3 goes to the right, E4 goes from this corner, touches this corner, and goes here. So the thing is, when you want to have the correct intersection pattern, the Peterson graph, you need E4 to touch this D4 at one point, and you need E4 to touch two other EIs, if you look at the Peterson graph. And so I couldn't very well draw it, so
it's okay. So then it stops at the red triangle at the left, or it kind of, okay, it's not very clear to me if it turns around or if it really stops at that vertex.
It turns around. I think it goes through and then turns around.
Okay, so it starts at the angled part, the angled edge of your diamond, and ends up on the edge that's furthest to the right.
Right.
No.
Yes. Right.
Oh,
right.
okay.
Yes.
Okay.
This is my intuition. It doesn't appear anywhere, and at some point we were totally confused if this intuition is right or not. Apologies for this. It's just to illustrate how the curves look like. Just try to, I mean, we will not use these. I never completed the affine geometric description of the Morricone, and there were things that were confusing me in this picture because all curves need to have positive intersections. So at some point we were discussing how to define correct intersection numbers. And to get everything correct, the Peterson graph, we need to have E4 is set to intersect only two curves, but you can never draw it correctly. So it intersects at the tip E1 and E3. It also intersects E2 and E5. But the thing is, it intersects E3 at 2 points, and we were hoping to define it in such a way that these two intersections cancel. So you need to assume one is plus and one is minus. But in principle, everything needs to intersect positively. So maybe you need to assume mod 2 or something. So there are some subtleties here in this picture, so we could now really figure out how to affine geometrically interpret the Morricone, but this is the naive idea to illustrate these curves. Sorry.
But like the fact that the images intersect doesn't mean that they actually intersect upstairs, right? In principle, the first intersection point when you're coming from the right of E3 and E4, that would be an intersection point of the two of them, because the cycles are different. But then immediately, I cannot see immediately that the next one, after it passed to the first red vertex, then I don't know anymore which cycle you're looking at. And it might be that if it's the same cycle, they might just miss each other, right? So,
right. So there are some subtleties. You need to choose a trivialization and what it means to intersect upstairs. So
okay. But
it's
okay,
sorry,
it's a nice picture.
It's a very nice picture. Yeah, you're right. Thank you for all the comments, and I hope I will be very happy to think more actually about this idea. It would be really cool to find a purely affine geometric description of the Morricone just by looking at the intersection patterns and almost toric-based diagrams. So if anyone's interested, I'd be very happy to talk about this.
Yeah, and just something like for you, it's quite important that you have this toric picture, the affine instructions on. That's why the red triangles are there as well, right? So it's not as if you somehow were to miss the affine structure of your toric manifold, it just became something for torus action instead, then it would not be a torus vibration, not a torus action. Then it would be harder to tropicalize things. Is that correct?
That's right, yes.
Okay.
Right. Thank you very much.
Oh, thank you.
Very good comments. So, in the two-dimensional case, if you look at what Calabi-Yau pairs, if you want to construct a canonical scattering diagram, we do is we associate a wall to every one-dimensional, codimensional one ray. And the wall crossing function is given by exponential k and v beta t to beta z to minus v, and v beta k is some constant, and v beta is the number of these curves we are counting that I was telling here. and V beta is the same and V beta. As an example, so we had these 10 minus 1 curves. The canonical scattering diagram for dp5 is on the left-hand side. So on every ray, you attach 1 plus ci inverse c2 ei, the curve plus ei. So it lives in, there are some 1 plus some monomial and some coefficients, which are elements of the Morricone Z2 curve classes. And what we do from the canonical scattering diagram, just to illustrate its importance, we construct a homogeneous coordinate ring just once you know what the canonical scattering diagram is. What we do is we actually perturb the canonical scattering diagram. We cannot construct it if we have a singularity at the middle. We push away the singularities. There is a chapter on GHK, gross-hacking Q, on reduction to the Gross-Seibert locus, where you need to push away the singularities. So you divide your walls into two walls, 1 plus C1 inverse C2 E1, and 1 plus C1 Z2 minus E1. And there are also, a final ingredient is some kinks of a PL function that leaves PL function on the tropicalization. And the kinks of the PL function are also from the Morricone. Once you have this reduction to the Gross-Seibert locus, which I draw here again, you can, out of this data, construct a mirror. And just telling this to illustrate why canonical scattering diagram is nice. I will not tell more about it in the next slides, but so this is around the origin, this is how the canonical scattering diagram looks like, and how they construct mirrors to look Calabi-Yau varieties. You look at any chart of the canonical scattering diagram. At this chart that I drew, you write your theta functions. So by definition, theta functions in the regular sense would be sections of ample line bundles, and in toric geometry, they will be in one-to-one correspondence with integral cones of the momentum cone. So if you have a toric variety, you know that each integral point would correspond to a section of an ample line bundle of your toric variety. And here theta functions corresponds to integral points on the fan picture of the local Calabi-Yau variety, which by mirror symmetry is expected to be the cone picture of the mirror to the local Calabi-Yau variety. So, and you write your theta functions by just following the wall crossing, and this is compatible but combinatory by looking at what they call broken lines. So if you fix a point here, you have 5 theta functions, as many as you have unbounded directions. Your theta 3 is just from the right-hand side. If you come with an unbounded edge, you stop here. So your theta 3 is Z3, your theta 4 is Z4. But if you come from below, you need to cross a wall. And so your coordinate Z2 changes when you want to come above, and Z2 changes to, if you would have only trivial wall crossing functions, Z2 will be Z4 inverse Z3 in the usual toric geometry, the toric relations. But you have non-trivial wall crossing functions, so you multiply everything with the wall crossing function times the kink on the wall attached. So you write all of your theta functions on a chart, and then you have all these relations between theta functions. For instance, you have theta 2, theta 4 equal theta 3 times something. And then you write everything with all these relations, you know what your homogeneous coordinate ring is. So the mirror family to dp5 is given by spec C of all these theta functions model these relations. So when you know all this data of what to attach to walls or your wall crossing functions, you can construct a homogeneous coordinate ring out of this data, and this will be your mirror family proposed by Gross-Seibert. Gross-hacking Q in dimension 2 and Gross-Seibert in higher dimensions. All right. So what holds true is if you look at a purely toric construction of a scattering diagram, which I denote by d sigma h, which is constructed as follows. So you assume that xt is obtained by a toric blow-up by x sigma, and to the toric variety x sigma, we purely associate a toric scattering diagram. We remember the data where you blow up. I will just go through this example. Like in dp5, we blew up at 2 points. On the two non-torically, we blew up on this toric boundary and on this toric boundary non-torically. So initially, I have the toric fan. What I do is I just turn 2 of my trivial rays into walls, which have non-trivial wall crossing functions. The rays where I blew up things in the toric variety, and I associate just some variables 1 plus T1x, 1 plus T2y to these rays. And then there is a purely combinatorial way proposed by Kontsevich, Soigelman in dimension 2 and Gross-Seibert in higher dimensions. And in this setup in higher dimensions, it's working particularly nice, which we explained in the work by Mark. When you have these two non-trivial wall-crossing functions, you need to add some non-trivial wall-crossing functions also to the other walls to obtain a consistent scattering diagram, to make sure at the end of the day, which we glue together from the affine patches, glues together to a nice algebraic scheme. And this consistent scattering diagram at the end of the day you obtain will tell you how your canonical scattering diagram will look like if you just tell how the TI variables are going to change in the Kerr class variables. And there's a description on how to change the TI variables into Kerr class variables. So this looks very much like our canonical scattering diagram. You need to change T1 to E1, T2 to E2, and so on. And this description is what we provide in our paper with Mark. So I will give an example. If you look at the higher dimensional case, which we considered, so if you look at P3 with two lines in the toric boundary divisor, this is a nice low Calabi-Yau variety. And if you blow up these two lines, X is blow up of L1 union L2 and P3. And then if you look at the canonical scattering diagram attached to XD, this low Calabi-Yau pairs in higher dimensions, the walls are contained in codimension 1 integral affine subspaces, and for every cone sigma and integral tangent vector and beta in the Mori cone of X should be X, you consider genus 0 punctured log maps in X of class beta intersecting D at a point with contact order B. So your problem is similar to dimension 2, you fix everything in one specific contact order at a specific marked point touching the boundary at one point your curves. And then you are allowed to impose the contact order negative, and then similarly you define your canonical scattering diagram as in dimension 2. On codimension 1 walls, you take the wall crossing functions exponential of some constant times these punctured log Gromov-Witten invariants t to beta z to minus v. And this canonical scattering diagram, the difference between dimension 2 and higher dimensions is in dimension 2 we never had negative contact orders, in higher dimensions you will have negative contact orders. The reason being, in dimension 2 we look at so you look at log maps whose form so in dimension 2 we want to consider n-2 dimensional strata of the moduli space. So in dimension 2 your tropicalizations could live, the generic point of the tropicalizations maps onto the in the 0-dimensional strata of the toric variety. And you cannot move it. It is 0-dimensional. Everything is 0-dimensional in dimension 2. In higher dimensions, we look at some, like in dimension 3, we look at one parameter families of curves. So we always consider n-2 dimensional families. And this means that your tropicalizations can move along a one-dimensional cone in higher dimensions. So your walls, the reason being, the walls we consider are n-2 dimensional, and the tropicalizations, the tropical maps, we want an n-2 dimensional family of tropical maps, tracing out these walls. So in higher dimensions, the difference occurs because, so if you have this AB vector, it never touches any of the boundary curves. It means you have contact number A and contact number B with these two respective divisors, but in higher dimensions, so puncture can occur if you hit the boundary of a cone. In higher dimensions, it's possible to hit the boundary of a cone. So that's the difference between dimension 2 and higher dimensions, and I'm happy to expand this if you would like. So, so the short story in higher dimensions, we need to consider negative contact orders. And what we did is we purely constructed a toric scattering diagram associated to the toric model of a low Calabi-Yau, and we constructed it as follows. Assume XT is obtained as a blow-up of a toric variety its hypersurfaces along its toric boundary divisor, then we can algorithmically, without using enumerative geometry, construct a toric scattering diagram associated to this toric variety as follows. So for every ray rho I of the toric fan, let Mi be the primitive generator of rho I, and let Hi be the set of connected hypersurfaces contained in the divisor d rho I that we will blow up to obtain our Calabi-Yau. And we define an initial scattering diagram consisting of walls together with walls are Wij, which are codimension 1 subspaces of Rn, together with attached functions which are of the form 1 plus Tij z to Mi. And we call these widgets, for example, if you look at our stereotypical example, P3 with 2 lines, our initial walls are going to be one-dimensional things living in R3. Sorry, codimension 1, two-dimensional things living in R3. And what are these things? These things are what we call widgets. They're obtained by taking the tropicalizations of these lines. So you blew up 2 lines along the toric boundary. So you take a tropical line, which looks like this, and you move the tropical line all the way along a ray, the ray that corresponds to the component of the divisor that you blew up the line at. So your initial scattering diagram looks like this in higher dimensions. So we define these widgets are higher dimensional walls, and we tell what the attached functions should be. And then we can complete this run. We run this purely combinatorial algorithm to complete this to a consistent scattering diagram. We add just 2 walls cross. We add more and more walls analogous to dimension 2. So it's more complicated because you have just higher dimensional things, and we made quite use of magma computer algebra to increase the amount of examples with time. So what we showed with Mark is you can use this purely combinatorial description. You can associate walls to the toric variety with Tij variables and obtain a consistent scattering diagram. And by changing the Tij variables to Morricone coefficients, you will obtain your canonical scattering diagram. And like in this 3-dimensional example, when I started with these 2 widgets, I need to start adding more and more walls to obtain a consistent scattering diagram, which means that when you look at a joint, which is where 2 walls intersect, when you take a loop around the joint, you want to take the composition of all wall crossing functions that you cross the walls along, and you want to get identity. So this is the final consistent scattering diagram for the example P3 with 2 lines you obtain. It has finitely many walls, which I illustrate, which I wrote in a table. But the interesting thing appears because we actually had infinitely many walls, but everything canceled each other essentially, and we ended up the minimal final consistent scattering diagram being only finitely many walls. And so using our technique to turn the Tij variables to Morricone coefficients, so here I have 1 plus T1x, it turned into 1 plus T to E1x inverse. So you invert the initial walls. And E1 is the class of a fiber of the exceptional divisor. So we had blown up line 1 and line 2. If you take a fiber of the exceptional locus and say its class is E1, so you trade T1 with that and T2 with E2, which is E2 is the fiber over the exceptional locus, and L is the strict transform of a generic line. So you obtain all these functions purely combinatorially, and you know that these functions correspond to these wall crossing functions with these Eij variables correspond to functions of the form. There's a form that is claimed by Grossi, but they should both this from exponential some constant and tau t to beta z to minus u, where n tau is a punctured log Gromov-Witten invariant. So by knowing these functions, we know this punctured log Gromov-Witten invariant. Let me say what I mean. So we have a wall with support E1 minus E1, E2. And I took the most complicated wall with support E1 minus E2. So these are the supports of the walls. I have a wall with support E1 minus E2 in my final consistent scattering diagram, and with a touched function this. So what do I do with this? I take the logarithm of it, and it should give me some constant times some punctured invariant. I take the logarithm of it, I obtain this formula. And what is the punctured invariant I'm looking at? I know that actually this wall crossing function, which would support E1 minus E2. So to obtain all the information you need about punctured log Gromov-Witten theory, you need to know the whole procedure. Knowing only the final consistent scattering diagram is not enough. So I knew when we ran the procedure, we knew that there came up two walls which are like in R3 are just these planes I drew in this picture is the xy plane and R3. The two walls 1 plus t to E1 x inverse and 1 plus 1 minus t to E1 x inverse were having support like shown, and the two walls cancel each other because one is plus and one is minus at every order. There's some cancellations, and when they cancel, I end up with E1 minus E2 wall with the correct thing. But what this says during the procedure that I have these two walls says that there are two different punctured log Gromov-Witten invariants coming up. And one comes up from the tropicalizations of one-dimensional families corresponding to the left-hand side and one to the right-hand side picture. What are these tropicalizations? So I have one-dimensional family of tropical curves, and in this picture on the bottom left. So I have two vertices and one leg going down, and I move this leg all the way around, and this traces out a one-dimensional region. So the tropicalizations of the log maps that I consider will be like this, and these are maps of the form. These are log maps. The image curve needs to be of class k times L minus E2 minus L E1. And these are, if you rewrite this, it's k times L minus E1 minus E2 plus k minus L times E1. So you have, if you look at a green line that I drew like this, passing through the first line at one point and meeting the second line and the other component at one point, if you look at the strict transform of this, it will be of class L minus E1 minus E2. If you take a k-fold branched cover with this, it will be of class k times L minus E1 minus E2. You want to add k minus L times E1. So what you do is you look at the inverse image of the point green line L intersects L1. You add, there are k points in the pre-image. You add p1s to L points among these k points, and you map it to the exceptional phi by E1. Then you get the correct curve class. And because you have L choices among k, you really have k choose L times this many maps like that. This is the multiple cover formula. So we essentially recover the multiple cover formula in higher dimensions, and this validates that our computation is correct. And the other family correspond to more complicated maps, which would be not possible to compute easily because the other family is like k-fold multiple covers of the screen line I tried to draw, and L-fold covers of this other line, and there's some contracted component. But so we obtain a technique that tells us what these kinds of maps, what these kinds of maps correspond to, without needing to worry about virtual stuff and just purely combinatorially. I apologize. I think I need to finish here. I probably might have lost you. You're very welcome to ask any questions afterwards, anytime. I'm always reachable. Thank you very much for your patience.
Thank you very much. I like that there are drawings. Often there are not enough drawings in geometry. We have like, okay, I have like 2 minutes for questions before I have to be elsewhere. But I don't want to.
We'll see while people continue to join.
Sorry, I don't want to take out the option of you to ask questions. So go ahead if you have any questions.
Can I ask? You were telling in the definition of the punctured log maps. So for log curves we have this nice classification by Kato of what the ghost sheaf looks like everywhere. Is there an analogous thing for the punctured case for a log curve, or is it just
exactly? Yes. So there is the in the punctured log Gromov-Witten paper, Abramovich and Grossi-But do the analogous theorem of Kato for punctured log maps. Yes, they describe the stalks of the ghost sheaf for also punctured points. Yes.
Okay, so I have the paper open in front of me and I can't find it, but maybe I will send you an email.
Of course, yes, please do. I'll be happy to talk about this with you.
Okay. Any further questions?
I do have a collection of them. What happens if you leave? Does everything disappear, or can keep on
So
asking
you know what?
questions?
Let's do one thing. First of all, I'm gonna stop recording. That way, any question and answer it becomes like just for us.
Okay.
Is that okay with you?